All right. Welcome everyone to our Tech Talks discussion on quantum computing in the financial sector. Thank you everyone for tuning in. We would like to start by thanking our sponsors, Cayman Tech City, who have partnered with Digital Cayman and Kirk ISS to make this ongoing series of events happen. Now, if you have any questions for our speakers today, please send those through the Digital Cayman Slack channel. You can also post your questions directly to the YouTube feed, and we'll answer those then. So every time a question gets asked, I'll reappear and ask those throughout the discussion. And we'll also have a Q&A session at the end, so make sure you keep those questions coming in. All right, I'm very pleased to welcome our accomplished speakers and know that we have a lot to cover today. So without further delay, I'd like to pass along the virtual stage to our moderator, Mike Philbrick, who is the CEO at Resolve Asset Management. Mike, over to you.
Thank you, Caitlin. And yeah, you took away my whole speech for myself. Anyway, just kidding. Yeah, my name's Mike Philbrick. Resolve Asset Management is just to give you a little background on me, is a quantitative asset manager, which is a fancy way of saying we use mathematical models and machine learning tools as a basis for managing investment portfolios. So you can imagine my interest is pretty keen here today. And we've got two pretty incredible guests, Dr. Terrell Franz from Harrisburg University, and Alex Kahn, Chief Product Officer at Chicago Quantum. And that is a solid handle. I like that handle a lot, Alex. So, I will leave it to you, the viewer, to go and look at their resumes. They're quite comprehensive. But the one thing that they have in common is we have two very passionate educators and authors joining us today. And they're both steeped in real life experience as well as academic expertise. And they both pride themselves on being able to take complex topics and make them approachable. Well, don't we have a challenge for them today in bringing us up to speed on quantum computing, its potential applications, limitations, the differentiation from traditional computational methodologies. So really excited to dive in here. And I'll just give you a little bit of a layout of how we're going to roll through this. So we're going to start with Terrell, and he's going to set the table. Why should we be paying attention? Give us an overview on the technology, where it's going, what's happening now. Then we're going to pause for some questions, and then we'll turn it over to Alex, and he'll dig into the portfolio optimization problem and using quantum computing techniques in application and solving that problem and challenge. So pretty excited. I'm going to turn it over to you, Terrell, to get us kicked off.
Okay, thank you, Mike, and Caitlin and Cayman Enterprise City for having us today. It's really good to be here. I am about to share my slides for you all. And I think you have them, right? Okay.
Roger that.
Well, let me start out by saying a warm greetings from Harrisburg, Pennsylvania in the United States. It's kind of strange, though, because it is -1 Celsius here. So I don't know if it's exactly warm compared to where you are. But just by way of introduction, if you're not familiar with Harrisburg, quickly, we're in the state of Pennsylvania. It's about a 4-hour drive, almost due west of New York City. And I come from Harrisburg University. Just quickly, it's a young university with around 7,000 students, and we started having program training in quantum here about a year and a half, 2 years ago. We give instructions for 9th graders all the way up to PhD level. So it's a new program, and we're having a lot of fun developing it. A connection with Cayman Island, our connection with Harrisburg and Cayman Island is the university participates in the annual STEM or Caribbean conference held at UCCI each year. Of course, this year or last year was kind of a miss, but anyway, that's the connection between Harrisburg and all of you down in the Cayman Islands. And I've been there a couple of times, and I enjoy I've been on Grand Cayman a couple of times. So thanks for having us. So today, in 15 minutes or so, a very quick 15 minutes, there's a lot to cover in this topic. What I'd like to do is really just try to give you a sense of why you should care about quantum technologies and or quantum computing. Now, I'll explain the slash there in a few minutes. Give you an overview of what these technologies are so that if you're in an elevator, you can quickly answer and simply answer a question on what this noise is all about. Give you a sense of where the technology is headed, where it is today and where it's going, and give you some advice, if I may, on what you should be doing now in your situation. Of course, everybody's different, so it'll be rather generic. But let me start with why you should care. Currently, quantum technologies really has a pretty small footprint compared to other technologies out there, meaning the numbers are small, the number of computers are trivial, the number of dollars being invested in quantum computing and other technologies, related technologies, is rather small relative to other things. So let's just start there. However, the delta, the change from year to year is beginning to really take off. And any foot race, that's a good place to be, where you're advancing very rapidly every year. And let me just give you some of the background on this advancing very quickly. Is essentially theories that have been around in physics for 100 years. We go back to the Albert Einstein era back in the 1920s, et cetera. Those theories have been lying dormant, if you will. However, in the past few decades, in particular the last 15 years or so, the engineering for turning those physics theories into practice has really taken off. And so what we're beginning to do is take these theories and actually starting to put them in practice. Again, I'll say it's still very early days, but the speed of change is rapidly advancing. Quantum devices have actually been in production for decades. We've had atomic clocks, those are quantum devices, and those clocks are getting more and more finely tuned. An MIR machine in the hospital is in fact a quantum device, a measuring device specifically. And right now, those trivial computing devices, the first quantum computer was effectively put together in 1998. Those devices that were created back in the labs are now starting to show up in areas, in places where the public can get access to these quantum devices, most notably Amazon AWS cloud service now gives everyone access to quantum computers, as does Microsoft Azure. So the other thing that is supporting this statement of running fast is investment into quantum technologies is growing very rapidly, both in the public and private sectors, as well as the scientific and commercial spaces. For example, the United States and the United Kingdom both have national initiatives. I won't get into the billions of dollars being invested, but I assure you they will be increasing every year, roughly $1 or $2 billion right now. The EU has a program called the Quantum Flagship. India has quantum in its national mission. Those of you who follow China, China is expected and has announced actually that quantum technologies will be in the next 5-year plan, which should be coming out publicly in the next few months. France, Canada, Sweden, Norway, and I can go on, have all made quantum technologies national initiatives to one degree or another. Just as importantly, we have companies like IBM, Microsoft, Amazon, Honeywell, and so on, all going in big time in this technology. IBM in particular is hiring dozens of people a month. They have a 5-year roadmap laid out for quantum computing. So they've actually made public statements of where we will be when it comes to IBM features and products in 5 years. So there's a lot of commitment growing in this space by big companies with lots of money behind them, and lots of scientists, et cetera, working on these projects. And something that's near and dear to my heart, because this is what I focus in on the most, is the ecosystem in quantum computing and quantum technologies is really starting to form. And what I mean by that is we're starting to transition from a community of highly skilled experts to being involved in these technologies to more of a the man or woman on the street can now start to program quantum computers, and so the people being engaged in this technology is really expanding quite rapidly. It's just not the PhDs anymore. So one thing that you should be well aware of is that is still very much unknown in the engineering in particular of quantum devices. But there's a huge, I call it a grand promise. A lot of, there's a lot of hype around this technology right now, which has both positive and negative aspects to it. But I believe, and many others do, that the conditions are right now, and in the near future for these quantum devices to have a substantial, and I use the word substantial, impact on society and human life. And don't take me, we won't solve all the problems in the world, but these devices will have impact on our society, no doubt, and the quality of human life in the biosciences. So in particular, right now, there's a lot of activity in national security and defense. Not a great topic to talk about unless you're in that business. But the militaries across the world are starting to really ramp up their investment and reliance on quantum devices. For example, the GPS system in the United States is being reworked to be using quantum devices. I hate to say it, but the GPS system is very easily hackable. So with quantum devices, a lot of that hackability, if I may go away. But there's tremendous promise in the development of life sciences and medication, and even to the point of personal medical personal health. The potential is really great in being able to customize medications for individuals. Again, I caution it's a grand promise. There's a lot of work to do, but these are some really fascinating use cases for this technology in some of our lifetimes. These are decades out. But today, there's certainly some impact, although there is some risk to this technology being applied to data security. And as Alex Kahn will talk about later on, and hopefully we have a discussion on quantum technologies and quantum computing's impact in the finance space. AI, artificial intelligence, is another area that should be dramatically impacted by these technologies. So just to give you a sense of what these technologies are, and we only have a minute or so to talk about this piece, but basically when we're talking quantum technologies, we're taking advantage of the quantum level physics that happens in the world. And I call it unusual because I grew up in the non-quantum world, meaning that, if I take a cannonball and shoot it out of a cannon, I can predict the classical physics, what we call Newtonian physics. I can predict where that cannonball will land if I know the speed, I know the weight, I know the wind direction, and all that kind of good stuff. So physics at our level that we can comprehend and see and experience is actually quite predictable, thanks to folks like Einstein and Newton and those folks. But underneath that, at the atomic level, at the subatomic level, it's actually a very different world down there. The physics that take place, if I shoot a cannonball, I don't know where that cannonball will be next. I don't know the speed of that cannonball given other conditions, etc. So I'm greatly simplifying this, but in short, the physics at the atomic and subatomic levels are very different than what we experience at our human level. And what we're doing now is starting to ask the question, hey, wait a minute, even though this physics is very different and quite odd, there may be some applications, there may be some things that we can do in our human endeavor that those weird characteristics may actually, if we can embrace this, if we can control those those strange physics, we might be able to solve some very difficult, complex, and interesting problems that we cannot address because of their size and their complexity using classical computers. And I'm talking, these big supercomputers at the research labs and everything. These quantum computers will easily surpass them in capability for some applications. When we talk about quantum technologies, there's really, I think of it as four really groups of technologies. One is the quantum computer. And these technologies, by the way, are very special purpose machines. These machines are not going to replace your laptop. They will not replace your phone, at least in our lifetimes that we know of. But you could consider these quantum technologies very special purpose. They're not there for your YouTube videos or your Zoom sessions, et cetera. But you could think of it as a quantum computer, which really takes what it brings to the table is allow us to do some very sophisticated and advanced mathematics. We have the notion of the quantum internet, and here using those strange physics at the atomic and subatomic level, we actually may be able to transport information like we do on the internet, but in a far more secure way. And I'll talk a little bit more about this in a second. There's also quantum metrology, which is basically measurement. So using quantum devices and the subatomic particles, we can measure things like distances, time, and many other things at a very granular level. One use case for these measurements, for example, a submarine in the ocean, actually when it's underwater, which I never realized, but it's pretty clear it wouldn't work, cannot use GPS to navigate. So the navies around the world need some really delicate and finely tuned devices to measure where their submarines actually are. They don't use GPS in a submarine. So these measurement devices, clocks and things like that are actually going to be very important when we get into, you've all heard of 5G, for example. Well, timing the clocks in those 5G devices are very important, that they're very precise and accurate. So quantum metrology is, I think, probably the most promising use case right now today for quantum technologies. And then fourthly, there's quantum simulations. And this is basically, in short, I won't go into much of this in any detail, but it's basically we're using nature to simulate nature. So one of the things that is a limiting factor in drug discovery and all those biomedical things is that our computers, although they're pretty powerful, they still are very constricted into the degree in which we can model phenomena in nature. Think human body growth, cell growth, cancer growth, and all that stuff. It's very difficult to simulate that at the level that we think that we need to simulate it. Right now, we can simulate things in the body, but it's using mathematical models. With quantum technology, we're actually using Mother Nature to simulate Mother Nature, which is just a fascinating concept if you think about it. So when it gets to, let me just focus in on the quantum internet, because this will come up in more and more in the press and media. It's basically where we can guarantee security in transporting data from one place to another. And this is a lecture in itself, believe me. Right now, when we secure data in the present internet, we're relying on very difficult math problems. So we have computational security. Well, with the quantum internet, essentially, and computational security can be broken if you have a powerful enough computer, like a quantum computer can break security in RSA right now. Not all security, but most of the security we use in the internet. The quantum internet will eliminate that issue because it's actually it's based on physics, and physics that is essentially uncrackable. I can go on for hours about this, but this is a big area that you'll see a lot of activity when it comes to quantum in the news. There's a lot of progress in this space. We have the notion of quantum key distribution. That's where we're taking the secret keys that we use between, let's say, a browser and a web server, for example. We share those keys using the quantum internet, and that is essentially perfect security. The key takeaway here, the bumper sticker is, the interesting thing is, a quantum internet is indeed hackable, but the difference is if someone does hack your message, you will know that. Right now, if you have somebody listening to, the Cayman Islands and a conversation going on between, Grand Cayman and one of the other islands, anybody can intercept that message and perhaps crack it. You would not know that you're being listened to. With quantum security, quantum internet security, you will in fact know if somebody is listening to you, which is an interesting thing to think about. It's also, by the way, let me just say, it has interesting implications in privacy if you think about that a little bit. The big one for today, most important, is the quantum computer. First of all, a quantum computer is not a general purpose computing device. It will not replace your laptop. Think of it, those of you who are IT oriented, think of it as a quantum processing unit, like a GPU might be, well, is in a classical computer. It's a computer used for very specialized purposes. It's not there to display, YouTube videos. The technology has been shown to work, but the big issue right now is we need more scale. So the engineers need to kick in with some more scale. And the other challenge right now is developing algorithms that need to be developed to actually use this different compute paradigm. I'm aware of the time, Mike, so give me another minute here. But the model to have in your head right now is, when it comes to the development of quantum computers, think of it as the 1940s, where for classical computers, where we had rooms full of vacuum tubes. Certainly, physically, a quantum computer isn't that big, but it's still very early days in development. So where are we headed? First of all, when it comes to quantum, there's still much unknown, and there's lots of things to be invented and developed in the near term. There is a grand promise. I am passionate. I do believe most of those grand promises will be accomplished, maybe not in my lifetime, but there is huge potential in this technology. And the conditions are right to have these quantum computers really have a substantial impact on our society. And I use the words human life very deliberately. What you should be doing right now, well, actually, there's increasingly in the quantum technologies ecosystem, there's an increasing sense of the fear of missing out. So we have a lot of people coming on board because there's a huge amount of potential here, and everybody, many companies are positioning themselves to take advantage of that. This is not something that you can plug and play. You put in your business model for today, and next year you'll be productive. That's not going to happen. There's a huge learning curve on this. But pay attention to the internet and data security issues coming on. Get yourself quantum aware. And what I would say, you need to have some sort of position on quantum, because this is going to appear very quickly when it does appear. And you need to know whether you're in or out, if you can think of understand what I mean there. So Mike, let me turn it back over to you for any questions you or others might have.
Yeah, I'm going to kick it off with a question. So in sort of the diffusion of innovation, sort of that adoption curve, where do you see us now? Is it innovator? Is it very early adopter? And where do you think maybe the crossing of the chasm might occur?
That's a good book, by the way. We're way, way, way down on the left of the curve, very early. And, in crossing the chasm, there's lots of different curves to deal with. So I would say in my opinion, we're kind of midway on the innovators curve. There's lots of other innovation to come, but we haven't. I think we're just starting to realize that we got to build the computer. We got to start to shift and start to think about marketing to the average business.
Right.
We're early days on that. It's
So
still very much a innovation space now.
in thinking about that and getting to the average person, consumer of this technology, are there any ways that we can help the average person move from sort of the deterministic thought process that we're used to the probabilistic framework that the quantum provides? Are there any sort of tricks or pieces of knowledge and wisdom that you can share from your teaching or that you share with your students to help sort of the average person get their head wrapped around this?
That's an excellent question, Mike. Very insightful. That's really what the community is working on right now. And guys like myself and Alex, and, we're teaching students, several times a week, and we and the entire ecosystem is trying to get our head around that. One of the interesting things about quantum computing in particular is that it's really at the intersection of advanced math, advanced computer science, and advanced physics, not to mention engineering. Moreover, I think the actual hardest part is the application space. So to me, programming a quantum computer, I don't think is that difficult if you understand how to abstract things in your mind. So to me, the bigger challenge is how do you take that capability, as you describe, this deterministic versus this stochastic capability, and put that into how do you develop a medication from that? See what I'm saying? How do you apply that to an optimization problem? I think that's the harder part. There is a lengthy and challenging learning curve for any individual. I've got 2 doctorate degrees, and I'm still working hard at trying to learn this technology and how to utilize it in a good way.
We have one question from the YouTube site too, is where do you see the quantum computing interacting with blockchain technology or crypto technologies? How are there, we knew we were going to get that question for sure, but maybe you can just maybe take a minute or two, and then we'll have to move on to Alex, but that'll be the last question for this part of the Prezzo. So quantum computing and blockchain tech.
There's a wide belief that there's something there, and this is getting back to the curve. Mm-hmm. The conditions are right. There's a lot of people thinking about that, but if to actually spell out a specific where that will go, it's still too early. But can we use a quantum computer for the data mining and things like that in the blockchain, to solve that mathematical problem? I am sure there are a lot of mathematical people trying to figure that out, because if you can use a quantum computer to do that data mining, you're going to do well. Right. But yeah, a lot of people are researching that, and there's a lot unknown.
Right, and we're very, very early in the innovation curve, so yep. To be expected. Well, great. Thank you. I think we want to be on time, and we want to leave lots of time for Alex to share a number of his insights as well. So, Alex, I'm going to turn it over to you, and Terrell's going to stick around too. So we're going to ask some more questions at the end. So everyone, hang tight, and it gets deeper. Go ahead, Alex. Oh, I can't hear you, Alex, or is it me?
All right, you should be able to hear me now.
Yes.
All right, so thank you, Mike, and thank you, Terrell, for doing a really great introduction to orient everyone in the areas of quantum computing. There is actually a lot of information, a lot of different ways of approaching quantum technologies, and just want to do a little quick introduction of how I got into it. And then we'll dive into the financial portfolio optimization portion. So in 2018, I was beginning to notice that quantum computers were becoming available online. So one of the quantum computers, D-Wave, made their system available where people could go in, sign up for free, and begin to start using quantum, the quantum system. And I was a dual major in engineering and physics and never really used my physics throughout my career. So when I saw this, I got really interested, and actually a lot of people who used to be science and engineering and physics majors are jumping back into quantum computing because their passion was in that area, and as they see these systems coming up, they're jumping into those. The whole evolution on quantum computing is still at the very early stage. There's a lot of work being done on the hardware. There's a lot of work being done at the software level. And yes, the goal is to make these tools available to the industry. But in the last 2 years, as we were getting involved, there just wasn't really a really solid real-world application that one could say, yeah, quantum computers can really solve something. There were small random number generators or quantum random number generators, but there were conversations around portfolio optimization, a lot of research on methods and mathematics around it. So when I was at one of the conferences, I ended up meeting Jeff Cohen, and we decided that we should partner up and actually take a real world problem and use a quantum computer to actually solve it. And so I think we're one of the very early teams that looked at the research that was already available in quantum computing, the hardware, the software that was already available, and we wanted to see what can we do. So we teamed up. Jeff Cohen is the CEO of Chicago Quantum, and I've got links and everything at the end of the presentation. So you can look up our team, our work, and our product, where we do actually financial portfolio optimization using quantum and other tools. I'm the chief product officer, and then Clark Alexander is a mathematician. He's also the expert in quantum mechanics and actually has taught quantum mechanics. So I wanted to make quantum computing a little more real. So we'll start out with the classical. So this is our evolution of current computers. And since the 70s, where we started out with a few transistors and integrated chips, the computers have been increasing in capacity, in performance, in the cycles, and really what's been happening is as the technology proceeds in the silicon-based chips, the transistors have been getting squeezed closer and closer and getting to smaller and smaller levels. Well, at some point what's happened is that we are beginning to get to a point where the transistors have become so small that there really isn't any room anymore. We're at the atomic level, we're at the beginning to see quantum properties actually show up. We're seeing quantum effects which actually are detrimental to transistors, because there are quantum properties like Heisenberg uncertainty principle, quantum tunneling, where the transistor, which is a switch and should be on or off, is beginning to get probabilistic. It might be on, it might be off. The electrons are tunneling from one end to the other where they shouldn't be going. So what we have seen is computer manufacturers have begun to take two approaches. One is parallelism, which is adding. So we've got a certain limit where you can go with the transistors, and then you just keep adding more cores. And as an example of this IBM Summit machine, this array of computers takes up about 2 football stadiums. It uses up about, I think, 25 megawatts of energy, which is about equivalent to what it takes to run 7,000 houses. And in order to continue to increase our computational power, we are basically not going smaller anymore. We're just going broader. We're just adding on more and more computers. The bottom picture over here shows that since we have gotten down to the atomic level, we can't go deeper anymore. So we're actually beginning to stack our transistors and come upwards and go into three-dimensional architectures. So with that comes quantum computers. So we're actually hitting against quantum properties anyway. So we don't have much of a choice. We might as well begin to think about, can we use atoms for quantum for computation in general? So here's an example of what systems are available now. When I started, none of these fancy pictures were available. A lot of stuff looked like lab equipment, and very small chips were available. But we have a number of companies around the world beginning to get into quantum computing: IBM, Rigetti, IonQ, and the different kinds of quantum properties that each of them are using. D-Wave, Microsoft Xanadu, and then I've not shown Intel, Google, Honeywell, and others. Looking under the hood, when you open up the box, what you see is certain quantum computers require very cold temperatures to run because you're eliminating all of the noise from the environment, the heat and the microwaves. You have a lot of shielding, and you also have to get down to where you can get the chip beginning to show superconductivity, where currents are flowing without any resistance. So these chandelier type of structures are called dilution refrigerators, and they progressively cool the temperature down to the chip, which is at the bottom. And the chip is almost close to 0 Kelvin, which is actually lower than the temperature in space. So here's some examples of chips and the dilution refrigerators. IonQ, on the other hand, does not need the cooling. It uses trapped ions. And if they do the cooling, they're doing it to remove interference, heat, and other things from the environment. But it's ions in a magnetic field, and this diagram shows the ions as they come into the trap. They're called ion traps, lighting up when lasers are hit on them. The Xanadu uses photonics, lasers or photons, and Microsoft is using a technology called Majorana fermions, which is a very complicated technology and has not been fully developed yet. D-Wave uses an annealing quantum computer, again using silicon-based superconducting qubits. But just wanted to give an idea of kind of what this stuff looks like. But it's available, increasingly becoming more and more sophisticated. I wanted to show that there are two different kinds of quantum computers, and at a broad level. The first one I'll call is the annealing quantum computer, which its main purpose is that you create some kind of an energy landscape. And these fancy diagrams, basically all they're showing is that you have different qubits, which is just like we have bits in a regular computer, there's qubits in a quantum computer, and these qubits interact with each other. In the case of annealing, you set up the qubits in a way that you have an energy landscape. You program your problem into this energy landscape, and all you're really trying to do is find the minimum of that energy landscape. So if, in a lot of machine learning problems, they use gradient descent to find the minimum. A lot of mathematical problems like the knapsack problem or shortest distance or shortest path problem, they require finding the minimum. And this annealing device, and the one we use is D-Wave, basically finds the minimum. Now, in a lot of problems, you're trying to find the maximum of something. So all you have to do is reverse the sign. and so you're then still finding the minimum, which is which is your maximum. So that's one set of primary quantum computer. The other development is going around what I would call is a universal or gate quantum computer. IBM, Rigetti, IonQ, a lot of others, and ones that are available through online cloud services like AWS or Microsoft Azure, use also gate computers. The purpose of a universal computer is that using gate logic, no different from our classical computers, where any computation can be done if you put in the right gates or the right logic. These quantum computers are specifically being designed to do any kind of computation. Now, I've seen some of the code needed just to do simple things like addition or multiplication gets pretty complicated because you're trying to put the gates that we do in classical computers with qubits, and qubits are somewhat expensive. So it's probably not the best system to do simple addition, but there are other things that we're seeing that it can do really well. And there's also now a combination of using classical computers and the quantum computer together, where the classical does what it does best and then feeds information to a quantum computer where we can see what the quantum computer can provide. So there's two different ways. There's different kinds of technologies being used. Some use electron spins, some use the energy levels within molecules, and some use the superconducting circuits where you have current flowing in either direction, and those properties actually are quantum properties and can be used for quantum computation. Really quickly, I mean, there's different kinds of material being used. Terrell already mentioned the nuclear magnetic resonance. There's like, for example, there's silicon germanium quantum dots, there's doped silicon, there's neutral atoms. The interesting one is a nitrogen vacancy center. They can actually take a diamond where a carbon atom is missing, so there's nitrogen sitting in there. And just the fact that nitrogen is within this lattice of carbon disturbs the energy levels, and you can leverage the difference in energy levels because of that nitrogen to actually build a quantum computer. And there's a lot of simulators that are using classical computation to simulate the math of a quantum computer. And that's what we use for experimentation and to get started. So there's a lot of use cases that are being investigated in quantum computing. There's optimization problems, which we will be talking about here. I've worked on the financial stock portfolio optimization. I've worked on fixed asset optimization, and any problem that can be converted into an optimization problem can then be solved with a quantum computer along with other solvers. Terrell already mentioned the quantum cryptography, and quantum machine learning is also being developed. There's a lot of sensors and quantum devices. Quantum chemistry is a big application where in order to either discover new molecules or look at processes that might be improved using specific catalysts, hopefully this whole area of quantum simulations will create new catalysts that can improve production of chemicals, maybe even photosynthesis, for example. The quantum random number generation is actually a technology that's been there for a little while now, and more are being discovered every day. So the Chicago Quantum team decided to focus on the financial portfolio optimization problem. We didn't really know anything about quantum computers when we got into it, and we actually were heading down the path of the gate quantum computers and realized that to put in a lot of assets and actually get results that we could show our customers, we had to switch gears and go to the annealing quantum computer, the D-Wave. All right, so I'm going to dig into the math a little bit. We won't be doing any real math because I would rather leave that to our to Clark Alexander, who's our expert in the mathematics. But simply, we start out with the Markovich formulation, which leverages the Sharpe ratio and produces an efficient frontier. The Sharpe ratio basically is saying, if you divide your expected return by the standard deviation, you get a ratio. And the efficient frontier basically maximizes a diversified portfolio using the Sharpe ratio, where for any given standard deviation or risk, you are finding a portfolio that would produce the maximum return. And we use the risk-free return over here, where at some point you have a portfolio that is the ideal or the optimal portfolio. But it's this frontier, this curve at the top that we are looking for, where you have, for any given amount of risk, you have the highest expected return. And this is what we wanted to do. We wanted to see, can a quantum computer give us this information? And would it be useful right now and practical for customers? So we're converting the math of the Sharpe ratio into an energy landscape, or converting it into a matrix math, where, as I mentioned, we're trying to maximize the Sharpe ratio, but in order to use a quantum computer, you have to reverse the sign. And so we're finding the minimum. And in this case, we're finding the minimum, which is the variance minus the expected return. And these are matrices, and I've given some definition. We can definitely go over that later. But we're taking the standard deviation, we're finding the variance and the covariance between the assets, and that creates a matrix of values, which is on this side. You've got the expected return, which is on the negative side. And then we created our own formulation where we can change the strength of the expected return to create different portfolios. And going further, you basically end up having a number of different values. We're summing up all of the variance terms, summing up all of the covariance terms, and these all end up in a matrix. We also have the expected return terms. And then we have a penalty, and I'll get into the penalty later on, but the penalty helps us to focus in on certain size portfolios. Like if you want 2-asset portfolio or a 5-asset portfolio or 10-asset portfolio. So I want to give you an idea of the landscape and the penalty and how we actually begin to solve this problem. So let's start out with a 60-asset problem, which is we have 60 different assets, and we want to find an efficient portfolio, and we can determine if we want a 2-asset portfolio or 3-asset portfolio or so on. So on the horizontal axis these numbers don't really represent the number of assets, but we start out with 0 assets on this side, on the left side, and then on the right side is the maximum number of assets. So the right side is the 60 assets. And in between, right in the middle, is 30 assets. So the blue landscape is what our matrix gives us. And as I mentioned, the system will minimize this landscape and find the minimum of that. And if you notice, the minimum of this landscape is right at 60 assets. So if we were to give this matrix to the D-Wave quantum computer, we'll always come back with 60, in other words, all assets. Well, that's not what we're looking for. So we have to change the landscape so that D-Wave will give us an answer that we really want. So what we do is we bend or transform this matrix so that, for example, in this picture over here on the top left, we have 10 assets. So we're saying, give us a 10 asset portfolio. Now, I want, in this diagram, it's not very clear that this looks like a complicated problem, but I want you to look at this number up on top. For 60 assets, there are this many. It's one with, I think, 18 numbers, one with 18 numbers ahead of it. That is the total number of possible portfolio solutions that can be, that are possible out of 60 assets. It's 2 to the power 60. Now, typically we know that the more assets you get, you're averaging out and you're not going to get your best asset portfolio. You're going to get something close to the market. So we know we don't need 60 asset portfolio. We don't need 30 asset portfolio. We want somewhere in the initial part is where we're going to find the best asset portfolios. So we can focus in on that side and not waste time calculating large asset portfolios. However, if we just look at how many possible solutions are available for just 10 assets, using the 60 assets to start with, that is 75 billion solutions. It sounds like a lot, but again, I mean, a classical computer can solve that. What gets more challenging is as you start going to like 20 assets or 30 assets. Now, if somebody was to say, what's a 30 asset solution? These numbers begin to get pretty large. And I want to compare with, we've gone to 3,000 assets, but putting this problem on a quantum computer, the maximum we've been able to do is put 135 assets. And out of 135 assets, if you're looking for a 30 asset portfolio, and you say, what's the best portfolio just in the range of 30 assets, you are looking for one solution out of 9.3 times 10 to the power 29. So this is the number of possible solutions that one can have out of 135 assets if you're looking for a 30 asset answer and you're trying to find the best. So when we try to create these landscapes, that's just a visual for us. The solution is not in here. It gives us an idea, so we see that we're shifting or transforming the matrix properly. As you can see in this, when the minimum over here is going to be the answer, the little red at the bottom. Now, probabilistically, we do a probabilistic sampling over here. We're not going to find the answer. That's why we're using the quantum computer. And there are this many solutions sitting over there for the 60, and for 135, it's that many. We hope the quantum computer will give us the answer because typically it's hard to find. A quick diagram of the matrix. So we do this math, we do the penalty, we end up with a matrix. And the matrix basically has the diagonal values and these non-diagonal values. It gives us a heat map of what this matrix looks like. It's a different matrix for the number of assets we're looking for. This is for 2, but if we change it for 3 or 4, the numbers change, and we can feed that into the quantum computer. I wanted to show you how the information actually gets embedded on the quantum computer. A 60 asset problem uses up quite a few qubits. So this is actually showing the structure of the quantum computer. And our math is fully connected. Every asset has a covariance term with every other asset. But the quantum computer doesn't have one qubit connected to every other qubit, so there's a bit of a loss. And so what happens is when we embed our problem onto a quantum computer, we are using up multiple qubits just to represent one asset. And we started out with the D-Wave 2000Q, which has 2048 qubits, but with 60 assets, we maxed it out. So this is the embedding for 60 assets, and you can see we've used up most of the area and the connections. That's about as far as we could go. I think we went to probably 65 is the maximum. Then D-Wave came out just recently with the next architecture, the D-Wave Advantage, and there's more connectivity between the qubits. In the 2000Q, one qubit was connected to 4 or 5 other qubits. In the new architecture, they also call it the Pegasus architecture, one qubit is connected to 8 other qubits. So it's an improvement, but one qubit isn't connected to every other 5,000 qubits. So the maximum embedding we were able to do was put 134 assets, which seemed to be the most stable. And then as we go further, it begins to get unstable. So that's why we could do 134. As I said, I mean, that's still a huge problem to try to solve. We've also compared not just the D-Wave, but we've looked at brute force, genetic, random sampling, heuristics, simulated annealing, taboo sampler, the hybrid quantum and classical together. We have tried simulated bifurcation. So we've tried all kinds of different methods along the way, and they're discussed in the paper. So here's the results. Our initial 40 asset problem, we were able to build the efficient frontier based on the Sharpe ratio calculation classically. That's the yellow curve or the yellow landscape. And you can see there's the efficient frontier, which would be the top edge. D-Wave, with our 40 assets, this was one of our first actual visualization. When we did the sampling, came back with those blue dots. So that is what we saw out of the quantum computer. We were pretty excited about it. I mean, it's not the efficient frontier, but it's kind of representative of the landscape, and that's where we started. So with many improvements and getting to understand the hardware, the embedding, and all of that stuff, this is where we were in October. And of course, since then we've continued to make improvements. The first one was July, probably June, and then this is an October result. Actually, this is an August result. So the yellow is the classical, the red is the quantum. So you can see that we are now beginning to fill the landscape, and we're actually able to see the efficient frontier using the results coming back from the quantum computer. And the blue on top of that is the results of using the classical genetic algorithm. Now, the genetic does a good job of creating the landscape, and it also comes up probably with the best results. I mean, we're definitely able to use the genetic to find the best result, but the D-Wave does an excellent job of filling in the efficient frontier, and we can decide how many asset portfolios we want, how much risk we want, and all of that. Here are some results, benchmarking that show how much time it took to get those results. Just very simply, brute force obviously takes the longest time. We have the Monte Carlo, which actually takes less time. And since we know we're looking for smaller portfolios, we can tweak the Monte Carlo to focus in randomly in the areas we want. So because of our problem, we can kind of do pretty well with Monte Carlo. It's not fully random because we're not going all over the place. We can focus in on 3 asset portfolios or 4 asset portfolios. Here are the D-Wave results. The D-Wave system gives back any number of solutions that you're looking for. You can do a sampling of 100, 1,000, 10,000. and it will give you a range of answers. It tries to find the lowest value, and typically we've found the lowest value, but then it'll give you other values as well. So there's as Jeff says, we get a spread of assets where if you said, if you gave your portfolio and said, these are the two that were the best, and you said, well, I don't like those assets, we can give you a whole set of answers that of values that are close to the best. And they might have assets in there that you actually either know of or would want to invest in. So here's an example of October 12 results. We picked MCRB and AX. And this result was produced, I think it was October 14th. And based on the Sharpe ratio, based on expected returns, those two assets were found by the system. And then you can see the behavior of those two assets for the next month or so. Again, we are looking at past data to predict future results, which is not really the case with the stock market. You can't really predict the future, but you can say based on the past, if things hold, how will that perform? So you can see the blue is AX, the yellow is MCRB. They seem to kind of do somewhat better than the market. Purple is the S&P 500. But then MCRB kind of trailed off over here. AX continued to do well. So in combination, while one is going up, the other one might be going down. In combination, that portfolio was the best answer out of the quantum system. And this is the final slide. I want to go over just quickly where we are and where we're headed. The red dots on the top are the D-Wave system, the annealing system. This vertical axis is the number of qubits. So you've got 5, 10, 100, 1,000, 10,000. So the D-Wave system obviously is was at 2,000, and then it's at 5,000 now. So it's making good progress. Single purpose, does the annealing or the minimization problem only. Then we at the bottom over here, we have the gate quantum computers, which have more errors, they're more tricky to create, manufacturing challenges. So that progress has been happening as well. You can see that there are less number of qubits. And again, the interconnectivity is much less between the qubits, but we're at about 50 to 100. I believe Google had a 100 qubit system, but I think we're kind of at the 100 range maximum. I have not used those systems. The best, the most number of qubits I've used is 16 on the gate operations. But you can see this all started before 2016, and now we're kind of sitting over here. So if quantum computers went with the same doubling every 2 years as predicted by Moore's law, they would follow this dashed line. So you can see to some extent they're doing potentially better than Moore's law. But again, there's a lot of errors that have to be fixed. It is also been discussed that for our calculations, we need about 1 million logical qubits. So this red line up on top over here is where we want to be, 1 million good, high quality logical qubits. But in order to get there, some people say it takes 1,000 noisy quantum qubits to get to 1 logical qubit, so 1,000 to 1 ratio. And so we would need to get to 1 million qubits to be able to solve real good, high quality problems. So I kind of drew this, extrapolated the data, created this trajectory. So we're making good progress, and every year I'm seeing a lot of new papers, but In order to get to about where I think we will be breaking RSA and really getting to some solid computations, could be anywhere from 2034 to 2048. But considering how different and new and somewhat complicated this technology is, I made the decision to jump into it so that when we get to this point, I, I understand it well. Okay, so I'm going to stop sharing. Well, I went a bit over.
Yeah. As we predicted, and nice and deep. Just a question: is there something in the quantum computing world that somehow addresses the challenge in the optimization process and its extreme sensitivity to the input values?
I mean, there's a lot of sensitivity throughout the process. I mean, in order to build the matrix, for example, you have to be able to create the math. A lot of problems don't convert into this matrix very well. There's a lot of effort being done by mathematicians on how do you take real world problems and convert them into the right math. Then if your matrix gets bigger and bigger, you'll notice that the best values, the difference between the best value and the next best value gets smaller and smaller. So the way our CEO tries to describe that is it's like climbing a mountain. And if your landscape, the number of assets or the number of variables in your problems get large, there's not much to hold on to. It's like a smooth mountain. And so you're not being able to move up this mountain very well because everything looks about the same. We have seen where when we get to 134 assets, the difference between the best value and the next best value is very small. And we're not sure if the quantum computer is precise enough to give us those differences. Though, I mean, the D-Wave is very precise, somewhat hides the errors from us. So we assume that we're getting good values. But there's mathematical challenges, there's precision challenges, there's the embedding challenge, and then the qubits themselves have errors and are not fully connected. They create these huge chains and the chains break sometimes. So you have an answer, but with broken chains, and I just throw the answer away, though sometimes we think maybe it's okay. It's sometimes a good value.
What do you think the experimental breakthroughs that might be necessary before we can construct a quantum processor that's sort of capable of surpassing, the present day supercomputer? What leaps do we have to make?
Well, so definitely the number of qubits. I mean, we're at 5,000 for annealing and probably 100 for gate operations. As I said, we need to get to about 1 million for gate computers. Because when we're doing any kind of problem, you're going to use up qubits. It's like when the transistor came out, we started moving from 1 transistor to 5 to 100 to 1,000 million, and now we're trillions of transistors. And it's the magnitude of transistors that are doing all of the heavy lifting, doing all the work, all the computation. So that's one. Then you need the qubits to be connected. There are certain properties that we're leveraging. So there are certain quantum properties like there's entanglement, which it's a quantum property. There's superposition, there's parallelism. If the qubits are not even connected, you can't have 2 qubits entangled, or you can't have superposition between those two, or you can't have parallel. I mean, there's technically, if you have multiple qubits and you do an operation on one, that is happening on all of the qubits at the same time. Well, if they're not connected, then that's in question. So in order to really get to where we think we see the advantage of a quantum computer, you will need really high quality connected quantum computers with lots of qubits. And isolating the qubit from the environment so that it maintains its quantum state is one of the big challenges. So, we talked about cooling down to almost 0 Kelvin. That is because
It's chilly.
that's because, think about it. We are actually, there was a time when people didn't even know what an atom is. We are moving, manipulating energies within atoms or photons or these quantum level subatomic particles, and those are touching other particles. They're getting bombarded with microwaves. They're getting bombarded with heat, right? Just the vibration of particles around it is destroying what we want. We want these particles to be isolated so we can use them for calculations. And the moment so what happens is we do our calculation on a quantum computer. We want to maintain this state which is isolated, and then we want to measure the end result. If you disturb it or measure it in some other way, in other words, touch it with another atom or bombard it with something else, you've destroyed that state, that landscape that we were trying to create. And so by the time we try to measure it, it's already destroyed. So error correction is one of the most important topics, and a lot of the work is also going into the error correction of these qubits, because there are errors right now, but the engineering challenge is to isolate.
Right. Go ahead.
Yeah, let me add to that. Just to take us back to the 1940s, many of us know that computers were based on vacuum tubes. And so those in the 1940s, we had the same problem. I think the engineering challenge here is far greater, obviously, because we haven't solved it with quantum computers. But vacuum tubes would burn out all the time. We'd literally have mothballs or moths, bugs in the vacuum tubes. So just keeping a computer alive in those days was very difficult. Now we're talking about individual atoms, individual specks, protons of light, which are far more sensitive than a vacuum tube.
Wow. Yeah.
Yeah, it's amazing.
That's incredible. And interesting. Is that where the word bug came from originally?
Actually, yeah.
That's fascinating. That's great. I did not know that. That's wonderful.
Grace Hopper, a she, by the way, gave it that term because there were literally moths in the ENIAC machines.
There's a bug in your computer, literally.
Yeah, literally. Yeah.
So we have a question, Alex, too. Is there any work being done in quantum computing with respect to sort of technical trading rather than sort of standard portfolio optimization? So, I know in machine learning, features and factors and things like that, you can sort of try and source those and see what's working. Is the quantum doing anything along those lines that you're seeing?
Yeah, there's a lot of teams. Yeah, there's a lot of teams working on all kinds of trading, stock market problems with banks, and I've seen options prices and predicting stock trends. So I know machine learning is obviously used to do time series and try to predict the future on a stock. We are also looking at quantum computers augmenting classical machine learning. And the thought there is also to leverage some of the quantum properties and see how can the quantum properties be used to predict. And I've seen, when you talk about hype, I've seen newspaper articles that say things like, quantum computers can predict the future. Well,
that's my ad. You saw my advertisement? No, I'm kidding.
So you have to just be careful about, what is your predictability of your machine learning algorithm based on all of the data that you're getting. And then one has to look at what is what have you added from a quantum standpoint, and is there a predictability or is there some enhancement in your predictability using some quantum math that you're using in there? And like I showed, we've been doing this consistently now since August timeframe. We've seen that our formulation, which is a very simple formulation, has about a predictability of maybe a month. Somehow the 1 year of data that we use to do our optimization seems to hold for about 30 days.
Right.
Yeah. But there's no guarantee on that.
That's fairly consistent with some of our findings as well. I mean, 1 to 10 days, and then it sort of tails off as you move to 30 days, and can be substantially less useful after that. So let's switch gears just slightly. We've got a couple of questions that occurred earlier as well. And one was how might we see quantum computing emerging in the Internet of Things? Is that something where we're seeing applications at this point, or how or what might they be in the future? Thoughts?
So quantum computers, so quantum properties are used for sensors. And so when you're talking about Internet of Things, any nanotechnology, anything that gets smaller and smaller and smaller eventually is getting into a quantum level. You can leverage quantum states and measure quantum states, and there might be a time when there are some devices that can somehow retain that quantum property at room temperature.
Right.
Because if you want to be able to have little quantum chips in your shoe, you need to be able to have it actually maintain its quantum coherence at room temperature. So there's a lot of also work being done on creating quantum devices that will run at room temperature, that don't require a dilution refrigerator. So yeah, I mean, I think that will continue to move forward.
Any thoughts there, Terrell?
Yeah, I mean, one thing to think about, so the Internet of Things, you could think of it as Alex mentioned, from the sensor perspective. But if you think about each IoT device as a node in a network, all right, now if you take 7 billion people on the planet and you figure, if not now already, each of us have 20 devices that we are attached to, if not now, pretty darn soon, you're talking billions and billions of devices that in theory are technically all connected. And so you think of it as, the number of states, the number of input devices that can be coordinated, manipulated, processed like a big machine learning problem. That's one thing that could play out 20, 30 years from now, is because we've got so many of these devices, you need to be able to process the information at the same time in unison. One device affects the other and all that. So we're talking decades out there, but conceptually, that's one of the things quantum computer can do, is deal with massive amounts of states on or off, if you want to think of it.
So I just want to add that, definitely the advantage of a quantum computer that's seen, in the future is being able to solve these problems with lots of variables. So as you saw with the Summit, IBM Summit, those are being used to solve huge simulation problems right now, but they are using up the power of a nuclear power plant. And, there's so, like 2 football stadium worth of, these computers that are running. That is not sustainable at some point, right? At some point, you just can't keep doubling the number of Summit machines. When we get down to this new technology with quantum computers, 1,000 quality qubits is 2 to the power 1,000 variables that it can handle. So, and it uses the energy of a refrigerator. So, at some point, these it will not be worth putting your problem on, classical devices.
If I can quickly, to build on that quickly and go back to that blockchain question. One of the expense of blockchain mining is the electricity, right? We know that. And so the interesting thing with a quantum computer, you could double, triple, quadruple, it's basically a fixed cost when it comes to electricity. It doesn't increase with the number of qubits, the number of processing bits you have. It's almost a flat line. So, that could affect blockchain processing because, your big cost in blockchain processing in data mining is taken out of the equation.
Yeah, and I guess the speed would increase substantially as well.
In theory.
In theory.
It has to. It has to, otherwise it wouldn't be useful, right? So.
Right. So we have one very technical question that's way beyond my pay grade, and I'll put it out, and then maybe we'll bring it back up to the surface to more applicable stuff. But so NP in the case of this question is obviously non-deterministic polynomial, and so I might ask you, gentlemen, to maybe define for us what a non-deterministic polynomial is, if that's possible. But what about NP-complete problems? What about NP-complete problems? Can they be solved with quantum computing? Do we need a different PC for different sets of NP-complete problems? What is the state of this?
Okay, so that's getting into complexity theory.
I misread our audience here. My goodness.
Juicy. Everyone just hung up, but give us a moment here, and then we'll come back up and have a few more basic questions, and then wrap up. But
yeah, so I think I think I will just very generally say that based on complexity theory, there are predictions that quantum computers should be able to solve NP hard, maybe NP complete problems. Quantum computers give probabilistic answers. So when you start looking at complexity theory and try to map quantum computers onto the NP hard, NP complete and landscape, it's not necessarily equivalent because this is a probabilistic device and the answers are probabilistic. So there's more of a probabilistic, there's a terminology for probabilistic hard problems or probabilistic problems. In that area, yes, quantum computers, if you look at the range of potential problems that quantum computers can solve, it kind of goes beyond NP to NP hard and into some of those other regions. But there's definitely a limit. And I would have to dig up my diagram to give an accurate answer to this question.
That's fine. Is thinking about probabilistic sort of outcomes sort of like the weather potentially? You know, the idea that it's going to rain today in these conditions, it's going to rain 70% of the time, and you know, you're well calibrated if the machine actually has rain occurring 7 times out of 10. Is that a way to convey this thought process to the average guy, or is it a little bit faulty, or help me?
Well, can I give a simple shot, and Alex will probably ramp it up a little bit, but the way I think about it is, think of it as, you know, when you're at the, the Baden sports stadium, right? And you got the football team there. And I don't know if you play the national song of Cayman Islands or God Save the Queen. I don't know what you do. But when you have a stadium full of people and they sing the national song, the national anthem, what have you, right? Let's say there's 20,000 people. Ultimately, you have perfect pitch. The song is perfect, right? But each individual person singing or not singing or singing a different song, actually, it all gets averaged out, but you have a perfect song at a perfect pitch. And that's how our classical computers work. We're dealing with electrons and all this kind of stuff buzzing around, et cetera. Now, quantum computer, we're saying, wait a minute, you know, each person in that stadium has something to add, some value, right? Some contribution to the song, right? So it may or may not, this may or may not make sense to you, but we're with a quantum computer, we're saying, hey, wait a minute, each individual can actually contribute something to the problem. Now, some people are wrong, some people are right, et cetera. So that's the way I think about it. It's probably oversimplistic, but if you can think of it with that model, I think that's what a quantum computer is doing, you know.
So are the error terms canceling out there, or is it something different in the quantum world?
Right. In the song, the errors are canceling out. Right. Okay. Now that's what we try to do with the algorithms. Right. We try to take those individuals and then kind of our algorithm manages that to give it a possible answer. And every time you do that, by the way, it's different, right? Because every time a person sings, it's going to be slightly different. Alex could probably give a more technical answer, but that's the way I think about it in my simple mind.
Yeah, so quantum computers do give probabilistic answers, and one simple way to think about this is if you could take your problem and reduce it down to a probabilistic answer. For example, is it going to rain tomorrow or not? Now that requires a lot of variables, right? I mean, you're starting out with a lot of variables, and eventually in your prediction of your weather is going to say there's a 50% chance of rain, or there isn't a 50% chance of rain. Now, does that mean it's going to rain? You know, you don't know. It's 50-50, right?
Yeah.
Similarly, quantum computers, when you create your landscape and they give you a probabilistic answer, you're getting something similar. And depending on your formulation, for example, if your formulation was, I've got a trucking company and I want to take certain routes, what's going to be the most efficient route, right? You would probably get a probabilistic answer that says if you go in this direction and take this route, you have a higher probability of saving fuel. And if you go down all of these other routes, there are lower probabilities of what you're trying to achieve, right? Or, efficiency, for example. So right now, a lot of the calculations come back with a probability. It's not a definitive answer. Only a few problems give you a 100%, this is the 100% answer.
Yeah, there's not many definitive, deterministic
Right.
versus probabilistic, right?
Right, and especially when we're dealing with huge landscapes, and when we are dealing with multi-dimensional problems that we're going to put on quantum computers, we are going to have to get comfortable with the discipline of giving probabilistic answers and interpreting from those probabilistic answers. I wanted to just quickly go back to the complexity theory. I popped up my diagram. And so polynomial time problems are the P problems. NP are the non-deterministic polynomial problems. And BQP is the quantum polynomial time problems. If you think about it, BQP goes into the NP area. It actually doesn't go into NP complete. So we will have to discover the set of NP problems that quantum computers can solve. And I think that is to be determined.
Awesome. So I'm going to do one last one, and then because there's the thoughts on Wolfram's assertion that the advantage you get from parallelization in quantum computing is lost from the amount of time you need to spend pulling together all of the parallel threads to get back to a classical answer at the end. Any thoughts on that?
Yeah. So okay.
That's from my partner.
Okay. Yeah. All right. Assuming
this is the last one though after this.
Assuming a perfect quantum computer where you have all of these qubits in superposition, and you're able to convert, as you do your gate operations, you're able to go from affecting all of your qubits in one go. So yes, definitely there's parallelism, and there is an advantage. However, if you think about it, if you could have 1,000 potential answers, you would have to sample at least 1,000 times to get the chance of seeing your answer at least once. So if you have 1,000 potential answers, you would have to sample 1,000,000 times. So if you have 1,000 variable or 1,000 potential answers, like we talked about the fact that in our math we had 1 to the power,
right,
30 potential answers. If I wanted to see all of them, I would have to sample at least that many times, because every time I'll only get one answer. Now, we only want the best ones, and we hope that the quantum computer is giving us the best answer. It's kind of filtering out all of the bad answers. So we only sample 1,000 times. I mean, I don't want to see all of my answers. I only want to see the best ones. So we'll sample 1,000 times, maybe 10,000 times. So I think that depending on what you're trying to do, I mean, you could, if you have 1,000 variables, you would have to, if you want to see the potential answer for all of those, you would have to sample, I don't know, 10 times 2 to the power 1,000. But that doesn't, I mean, that's not how you're going to really make use of a quantum computer. Your formulation and how you are really using it will have to be determined properly, where within 1,000 or 10,000 samples, you're actually getting an advantage.
Amazing. I'm going to ask one last question for both of you, and it is just a more general question. In the realm of quantum computing, if we're talking to two different sets of people, one is business owners or entrepreneurs or companies that are thinking about, well, how do I need to think about quantum computing and its applications to me? What should they be doing? And then next, for young people, for young aspiring computer engineers, how should they be thinking about quantum computing in terms of their careers and their career trajectory? And how might they think about incorporating that and what direction to take, how much to focus on it? So two parts there, really quantum computing and how it relates to business and how it relates to young people coming up in the workforce.
You want to take that, Darrell?
I'll take it first and punt it over to Alex quickly. As I try to get to, from a business person, I'd say the majority of us should just, become aware, watch what's going on, pay attention. It'll hit us in the security space sooner, but the deep technical people, the Googles and so on, and Microsoft, they'll take care of the details there for you. But there will be some changes with security coming up rather near term, but it may just be noise to a CEO. But if you're in finance, though, I would say, I don't think we really went into it too much, but if you're in finance, this is a really important place to pay attention to. Goldman, JPM, Wells, et cetera, all the big boys with the with the high margins, they're investing in this.
Citibank,
and
yep.
And the little guys, we gotta, in finance, we gotta compete with those folks. So do pay attention because the rug could get pulled out from underneath you. It won't happen today or tomorrow, but the young person, though, if you want a career that has legs, that will grow, that is hard, that is difficult. So the barrier to entry is rather high in this field. If I was a young person, I would take it. That is a huge advantage. If you're willing to, work hard, this has a high barrier to entry, which means less competition, which means if you're willing to do the dirty work, if you're willing to do the hard work, you will have an incredible career.
Yeah, and a significant advantage. Alex?
Yeah, I would answer that with, I was an executive in companies where I was responsible for portfolio optimization and picking technologies that we would bring into IT. I will say that, a lot of industries are followers, and they will not pick anything that is too far out there, and they're not going to spend money on it. They're not going to pick it, and they typically watch for their competition, their other companies in their industry to adopt a certain technology before they get in. But on the other hand, I mean, I've had this debate and discussion around first mover advantage. I mean, quantum computing can potentially have a first mover advantage, which by the time technology becomes commoditized, that advantage is gone. I mean, and sometimes it takes just a few years. So for companies, that really want to leverage an advantage in quantum computing, you would have to be paying attention and stay ahead of, what's available, what's possible. Have, scientists working in looking at your formulation, converting your formulation into, is there something that could have an advantage in the near future if you were going to a quantum computer? Because, for example, I mean, we just got the 5,000 qubit computer that plopped, this year. And if we were not ready with the knowledge and formulation for the 2,000, we would never have been able to get onto the 5,000 within, I mean, literally, we didn't have to do anything. We, because the default system switched on our execution, and our formulation just switched to the 5,000. Now, if we were not there on that day, we would not have been able to go from 60 to 134 in one day. So, I mean, and a lot of other companies are coming up with their own formulations and on their own hardware. So there's a first mover advantage. And depending on, these various banks that are working on this area, looking at options, looking at fixed asset, they might have some formulation that can produce some results, and they're just waiting for the right hardware.
Right.
So that's what I would say on the application side. And on the as far as students are concerned, somebody who is looking for a career path that involves science, math, hardware, computers, applications, I mean, this couldn't get any better. And the amount of areas that one can go into is astonishing. I mean, you can go into a chemistry field, do chemistry simulations. You can go into the finance field and then do financial optimization. You can go into hardware and photonics and error corrections and all of that stuff. I mean, I think this is going to open up a lot of fields that we don't even know about, just like the computers, chips opened up the internet and Zoom. Who would have imagined Zoom conversations, when in Bell Labs, Shockley was, looking at silicon transistors, right?
Yeah.
So this is, and we don't know where this is all going to go. Someone looking at 5 years, they're going to go into college for 4 years, maybe 5 years to get into a PhD. 10 years from now, I mean, they could be in high demand, right? I mean, they don't know what could be happening at that point.
Well, we're right in that innovator part of the adoption curve, and that accelerates quickly. And there are no other people with those skills potentially. So you get dragged up the corporate ladder, if you will, pretty quickly if you're willing to take that innovator risk, I guess, from an educational perspective.
That is true.
Right. Yeah, it's not without risk. Absolutely.
Yeah. Well, gentlemen, I really appreciate the time you've taken today. We're, over an hour and 30 minutes. We kind of had a sneaking suspicion that we might end up a little bit over time, and I'm okay with that. And I appreciate you gentlemen being so generous. Caitlin, I'll turn it over to you.
Yeah, thank you all for taking the time out of your busy schedules. That was an amazing discussion. I definitely learned a lot. It was a difficult discussion, but it was really good to learn more. And Mike, thank you very much for moderating this session. That was great. For anyone who's tuning in, please continue the conversation online. We'd love to keep the conversations going. Cayman Tech City and Digital Cayman, they're on a mission to grow Cayman's tech sector. So that's why we're doing events and discussions like this. So please do get involved. Visit digitalcayman.com for more details there. And finally, a special shout out to Kirk ISS for their technical support today. All right, I think that wraps everything up.
Cue the outro.
Yeah.
Do you have cool outro music where we're gonna,
Next time.
All right.
All right. Bye, everyone.
All right. Thank you.
Bye.